Assalamualaikum and selamat sejahtera. This time, we will discuss about a three-phase, uncontrolled full-wave rectifier with resistive load. We will start our discussion with the circuit topology of the full-wave rectifier. Based on the diode's configuration, this circuit is called a three-phase, uncontrolled bridge rectifier. As similar to the single-phase bridge rectifier, this circuit also requires a pair of diodes to conduct a full-wave AC current. Since there are three line currents in the three-phase power system, therefore, the three-phase bridge rectifier consists of 6 diodes. 3 diodes at the top and other 3 diodes at the bottom. Before we proceed with the principal operation of this rectifier, let's do some revision related to the commutation lines discussed in the previous video. As discussed before, there are 3 commutation lines in the operation of a three-phase half-wave rectifier. These lines are referring to the intersection points between two positive half cycles of the three-phase voltage waveforms. However, since a three-phase full-wave rectifier can rectify both positive and negative half cycles of the voltage waveform, thus, we need to consider the intersection points in both half cycles. According to the waveforms, we can see there are 3 intersection points in the negative half cycles. Hence, these points are also considered as the commutation lines of the full-wave rectifier. Next, I want to point out the difference between the output voltage of the three-phase half-wave and full-wave rectifiers. I will explain it using the equivalent circuit of both rectifiers. For this discussion, we will consider the rectifiers to conduct the red line current. To do so, diode D1 in the half-wave rectifier and diode D1 and D2 in the full-wave rectifier will turn on. Eventually, we will have these equivalent circuits. The obvious difference between both circuits is the number of voltage sources. In the half-wave rectifier, there is one voltage source, while the full-wave rectifier has 2 voltage sources in the equivalent circuit. To see the impact of these voltage sources to the output voltage, we need to analyze the circuit using KVL. Based on the output voltage equations, we can see the output voltage of the half-wave rectifier is equal to VR, which is a phase voltage. Meanwhile, for the full-wave rectifier, the output voltage is equal to VRB, which is a line voltage. Therefore, we need to sketch the three-phase line voltage waveforms before we can sketch other voltage or current waveforms of the full-wave rectifier. Now, I will show you a trick to convert the phase voltage waveforms to be line voltages easily As mentioned before, the line voltages are leading the phase voltages by 30 degrees. You can calculate this value by subtracting the phase angles in both voltage equations. Due to the leading condition, we need to shift the y-axis to the right by 30 degrees. As a result, the new y-axis is located at the first intersection point, and the old y-axis is now labeled as negative 30 degrees. At this moment, we already have a complete waveform of line voltages. Therefore, we can change the voltage level and the amplitude values.